よろしくお願いいたします。
Good afternoon, everyone. Today, we'd like to present our research on molecular design and synthetic study for stable benzene. The contents are described here. We have been interested in organic synthesis. At first, our teacher introduced us a book, Organic Experiments, which was for the university students. In the book, we found a unique compound that was tryptizane. At first, we prepared tryptizane according to the book. While studying, we were also interested in a highly reactive precursor of tryptizane. That was benzene. Do you know what benzene is? It is an intermediate derived from benzene by removal of two ortho hydrogens. It has triple bond, carbon-carbon triple bond here. Usually, triple bond is linear. However, benzene has quite strong triple bond. Therefore, it is quite unstable. In other words, highly reactive. It can be generated for a short period of time and cannot be isolated yet. Here, we settled our objective. Our final goal is the synthesis and isolation of a benzene derivative. And for the synthesis, we design the original molecule and the synthetic route. Next, let me explain the outline of molecule design. Here is benzene. The strand triple bond is naked and reacts easily. If we add bulky substituents, the triple bond is protected from the reaction. This methodology is called kinetic stabilization. We decided to put such bulky substituents to obtain stable benzene. There are some known methods to generate benzene. One is the elimination, and the other is the hexadehydrodeoxide reaction. We apply the latter reaction. Hexadehydrodeoxide reaction is a thermal reaction of diene and alkyne as shown here. If the reaction occurs, a cyclic compound forms like this. This compound can be regarded as benzene by rearrangement of the bond like this. Next is our fast molecule design. This structure is the model of our target benzene. Let's see the reaction in reverse. In order to prepare this molecule, we need to get this precursor. So we decided to prepare this molecule. We could obtain the precursor having bulky substituents by coupling of two terminal alkynes. Then we tried synthesizing benzene with a reaction of this precursor and with alkyne. However, we could not identify the products, so we found that intermolecular reaction does not proceed as we expected. So we moved to an intramolecular reaction. Next is our second molecule design, intramolecular reaction. Intramolecular reaction means that we need to create a single molecule including all the reaction units. We decide to synthesize a cyclic compound. This is the outline of the synthetic route. As a synthetic strategy, we start from the triple bond compound, and then terminal carbon-carbon triple bond units are connected to it. Then we close the ring by a coupling reaction. Finally, hexadehydrodeoxide reaction produces benzene. Then we discussed the ring size. We investigated 3 candidates, ring with 5, 6, or 7 carbons. we made various molecular models and found the following features. First is the difficulty of the ring closing reaction. In the cases of 5 and 6-membered ring, the terminal parts overlap with each other, so the coupling reaction seems to be difficult. Second is the ring strain. Since the carbon-carbon triple bond tends to be linear, the precursor having 5 and 6 carbons are highly strained. Third is the protecting ability of bulky substituents. In the case of the 7-membered ring, the bulky substituents are located the closest from the benzene unit. It is preferable from the point of the protection. Through this discussion, we decided to synthesize 7-membered ring molecule. Finally, we designed the target molecule to be a 7-membered ring. To obtain this molecule, we have to prepare a cyclic compound, like this. Now we would like to explain the specific molecule design. To design the specific route, we discussed some synthetic tactics. We used ether linkage, which is easy to make compound to carbon-carbon bond. Also, we use benzene rings to which it is easy to introduce various functional groups. Through synthetic route, it should be easy to introduce bulky substituent. Here, you can see the synthetic route. This route, composed of 6 steps, was originally developed by us. The raw material is carbon-carbon triple bond compound as shown here. In the first step, the compound reacts with methyl salicylate to obtain compound 1. Then compound 1 reacts with this linear reagent to obtain compound 2. Linear reagents have some merits. It enables us to change bulky substituents easily, and various bromo reagents are commercially available. Next, compound 2 is coordinated to form compound 3, and then compound 3 is connected to the carbon-carbon triple bond units by the reaction of acetylide to form compound 4. Next, compound 4 is coupled by using coupling reaction to obtain macrocyclic compound 5. Finally, compound 5 rearranges by heating to form benzene 6.
Next, I would like to talk about our experiment. The first step is Wilson et al. Synthesis. When the product was recrystallized, yellow pale crystal appeared. Through this reaction, we succeeded in synthesizing compound 1. This is a novel compound. Here, you can see the X-rays crystal structure analysis of compound 1. You can see the same structure as the one we expected. The distance and the angle around carbon 1 and carbon 2 support that carbon-carbon triple bond character. In the second step, compound 1 reacts with this green reagent. The product was treated with acid. Finally, we get a crystal. We succeed in synthesizing compound 2. This is a novel compound 2. Here, you can see the mass spectrum for compound 2. These peaks correspond to compound 2. The third step is a coordination. We get a mixture, so the mixture was separated by chromatography. And finally, we get 2 compounds. Here you can see the IR spectrum for two compounds. Absorption peak around 3,500 wave number correspond to hydroxyl group. Therefore, the upper figure suggested that the one compound has a hydroxyl group, and the lower figure suggested that the other had no hydroxyl group. So the lower is plausible for compound 3. However, we have another data to confirm compound 3. So we have to confirm the compound 3 by another way, such as NMR and mass. Next, I'd like to talk about conclusion and future subject. We have designed an original molecule for the purpose of preparing a stable benzyne derivative, and we have designed a 6-step synthetic route to prepare the target molecule. The first 3 reactions had been performed, and 3 compounds were identified. As a future research, we will investigate the synthesis of a target molecule and confirm the formation of stable benzyne. If we don't isolate the target molecule, we will design another molecule for the stable benzyne. Thank you for Professor Shinji Inamata at Fukushima University for the help in the analysis of compound. These are references. Thank you for your attention.
ありがとうございました。ただいまはオーラルプレゼンテーション6ベンザインの単離を目指した分離設計とその合成に関する研究、福島県立福島高等学校の皆さんでした。それでは次冒頭に移らせていただきます。ご質問のございます方、どうぞ挙手でお知らせください。はい、では、あちらの一番端にいらっしゃる眼鏡をかけている白いワイシャツの方にお願いいたします。
冊子では化合物1を合成するときにいくつか生成物が生成していたということなんですが、どのような生成物が生成していたと考えられますか？
はい、質問ありがとうございます。おそらく出発物質から最中酸メチルを使って反応させたのですが、60度の温度でやったんで、最中酸メチルのカルボニル炭素のあたりにその最中酸メチルの OH が攻撃とかして壊れてしまったのではないかというのが考えられます。
はい、ありがとうございます。
ありがとうございます。もう一方いらっしゃいました。どうぞ挙手でお知らせください。ではそちら真ん中の方よろしくお願いいたします。
大変素晴らしい発表でした。私からは3点気になる点がありまして、できた化合物まではいいんですが、その先のスキームでアセチレニル基の導入とあるのですが、この導入する分子はどのように作成して使用するのかということと、5番の分子の安定構造から考えると、加熱だけでイルサウダーが反応して6番の分子ができるというのが、構造的に考えづらいというふうに僕は考えました。最後に、引用でウィキペディアを使うっていうのは、引用にならないので、ウィキペディアの引用している点を引用した方がいいのではないかと考えます。お願いします。
ありがとうございます。ウィキペディアのから引用のウィキペディア自体も引用されているということで、ウィキペディア引用してウィキペディアに書かれていることのその引用元で僕たちのこの発表での引用元にすべきだということで、
そういうことです。
ありがとうございます。
人流器の導入体4番でよろしいですか。はい。これは実際にナトリウムアセチルドを 試薬として売っているものを、買ってきて、実際に文献としてそのような反応があるので、それを用いて行いたいと考えています。よろしいですか。次に、2段階、最後のところの多分、イレザルタ反応がいらないのではないかという、ご指摘なのだと思いますが、実際に私たちはまず、一回これをやってみたいと思います。そこでもしご指摘のようにうまくいかないのであれば、もちろんそのディレザルタリアクションが電子吸引線の、そういう感応器を入れてあげると行きやすくなるということを僕は、反応がいくということを行きやすくなるということを知っているので、またルイス酸などを入れると良くなるという、文献もあるので、その点に関してはさまざまな方法を、模索しながら、試していきたいなと考えております。
はい、構造的にディレザルタが起こらないのかということが気になったんですが、
構造的にですか。
構造的にです。
その点に関してもやはり
これが試していくということで、
誰もまだやったことないので、それに関してはまだ未知の点が多いので、実際に私たちでやってみて、もしできなかったら、それも一つの大きな成果かなと、私たちは考えています。
はい、ありがとうございます。
それでは以上でただいまのオーラルプレゼンテーションを終了とさせていただきます。オーラルプレゼンテーション6、ベンザインの単離を目指した分離設計とその合成に関する研究、福島県立福島高等学校の皆さんでした。